Good morning, everybody, and welcome to my talk. It's so nice to be here at the Zen Summit again this year. So my name is Wei Liu, and I'm one of the committers of the Zen project. And I had been working on all sorts of Zen-related projects in the past few years in all sorts of areas that is imaginable in the Zen ecosystem. So the topic I'm going to cover today is called secret-free hypervisor, now and future. Given that this is only a 25-minute section, I'm going to keep this talk at a very high-level overview of what is going on. I think the details aren't that interesting to the general audiences anyway, so that I'm not going to go into very specific examples on how a specific piece of code is constructed or how it should be modified. But if you are generally interested in this sort of questions, feel free to talk to me after the talk, during the breaks, whatever. So this talk is relatively short, so only have a few agendas. The first is, of course, to answer the questions. Why? Why this project? Why secret-free hypervisor? What benefits does it bring to the table? And then the second part of the talk is about what is involved in this project, what problems or issues are we trying to solve, and how we are going to solve those issues. This part is further split into three subsections. One is the primary targets, which contain secrets in the hypervisor. And then I'll give you a taste of the scope of this project. And then I'll give you some examples on what is involved in actually building code for this project. And finally, there's going to be a very short status update on various bits of this project. So why? We ask this question. Why do we need secret-free hypervisor? Why is it useful? So this project is basically prompted by the Spectre and Meltdown fiasco. Since 2018, we have actually seen quite a few hardware bugs and side-channel attacks based on speculative execution. And after dealing with the mess caused by Spectre and Meltdown, which was certainly not very fun, the upstream community asked the question, how can Zen defend itself against this class of bugs? How can we avoid playing this whack-a-mole game in the future? So we kind of know that side-channel attacks are here to stay as long as there are shared resources in the system. And then hardware bugs and hardware bugs are also here to stay, given the complexity of modern CPUs. And it's a bit unfortunate that all the well-established isolation mechanism and security boundaries, such as page table and kernel user space isolation, are broken and cannot really be trusted. So let's rethink Zen's strategy against this class of issues. So the attacker actually just wants to extract secrets from the hypervisor. What if there's no secret to leak in the first place? So this thought actually opens up a slew of opportunities for architectural changes and improvement in the Zen hypervisor. But it also, of course, has other implications as well. As of a few months back, we have identified at least 2 primary targets which contain a lot of secrets in the hypervisor. There might be other targets, but for now, let's focus on these 2 targets. The first target is the direct map. So Zen, just like any other operating systems, has a one-to-one mapping of all physical memories in the machine. This mapping is mostly there for performance reasons. It's not strictly necessary for the properly functioning of Zen. And if you can read from that mapping, you can read everything in the machine. And the second target, which contains get secrets and Zen secrets, is the stack. Stack in Zen at the moment is allocated from an always mapped heap called Zen heap. Zen heap is visible to all CPUs. And we consider stack content sensitive in nature. So now that we have identified all two targets, what are fixes? To summarize the physics in a few sentences, the following needs to be done. For direct map, we would like to remove it completely. That means Zen would need to map and unmap pages as required when it tries to access memory. For stack, we should switch to use the physical CPU stack, which is not visible to other physical CPUs in the same machine. That's so easy, you might say, because it only takes less than 1 minute to describe the solution after all. Or is it really that easy? So for starter, Zen's code is very interesting, shall I say. Its academic origin and organic growth over the years brings some very challenging aspects. Firstly, some of the code is rather messy or not very modular. The upstream community has done quite a bit of work in that area to clean things up in the past 2 years. But trust me, there's still a lot more to be done. Secondly, we don't have that many design documents lying around, and a lot of code lacks critical comments. It's often the case that one will need to reverse engineer Zen with several different versions of Linux alongside as references to figure out what the expected behavior of the hypervisor is. And lastly, there has been quite a few instances of interesting looking code and design decisions within Zen. If you stare at a piece of Zen code for too long, you might find something that's unspeakable. So all of these add to the complexity of this project. And there isn't really a way to get around them other than to just keep calm and carry on, really. So I basically made this graph from all the Jira issues I created, just to give you a taste of the scope of this project. And frankly, without breaking down things like this project is just intractable. So up the top, there's this secret-free Hypervisor project, which acts as the umbrella project, and it's broken down into several smaller projects down the line. The arrows in this graph means depends on. So for example, to finish the secret-free Hypervisor project, we will need to finish its two dependent project, remove direct map, and use per CPU stack. But please keep in mind that this graph is by no means complete. New dependencies may come and go in the future. Each of these leaf projects is hopefully a standalone project all by its own, but some of them inevitably intertwine with others at the code level. So far, my approach has always been, let's start from the leaf projects and then see how it goes, and then modify this graph as I go along. So this is actually what I got today. So you can see it's already growing into a very substantive graph. The next thing I'm going to do is to go over some of the projects so that I can give you some ideas what is actually involved in each of them. So let's take this use DOM heap page for page tables as an example. This is going to get a bit deep into Zen code, and if you don't really follow the reasoning, it's fine. Yeah. So currently, the page table in Zen uses Zen heap pages. The Zen heap pages are always map pages. And all the page table manipulation code is written with the always map property in mind, which means that when you try to access page tables inside Zen, you don't actually need to map them. You just call a function which does some pointer arithmetic and extract fields from one pointer and then follow it down to the next level or back. So it's really convenient. But now we want to use DOM heap pages for page table. DOM heap is another heap inside Zen. The most significant difference from Zen heap is that DOM heap pages aren't always mapped. So when you want to access a page from the DOM heap, you actually want to map it, access its content, read or write to it, and then unmap it after use. So in order to switch the page table code from using Zen heap pages to DOM heap pages, we need to painstakingly rewrite all the internal APIs and dependent code without breaking bisection in the middle. And then more importantly, the changes need to be broken down to reviewable patches. I don't think a patch which touches 20 files and maybe 1,000 lines in length has any chance to get merged. And then after we finish the use DOM heap for page tables project, we can then move on to the one level up to implement Zen heap with vmap. Okay, there's some other new words in this project, but yeah, let me try to explain them. So as I mentioned before, Zen heap has the always map property, which means, there's another detail. The Zen heap in Zen is also closely connected to the direct map in Zen. So we try, when Zen heap is initialized, if we try to map as much memory as possible from the guest, which means today Zen heap itself contains quite a lot of secrets. So we would like to ideally remove as many secrets from the Zen heap as possible. But at the same time, because Zen heap has a very nice property of always map, a lot of existing code uses the API quite a lot. So here's where vmap comes into play. Vmap provides long-lived mappings. Oops, sorry. Wrong page. So vmaps provides long-lived, globally accessible mappings. So if we implement Zen heap on top of vmap, we can have the nice property of always map from the caller's point of view, but at the same time, we don't map everything in the heap. So the biggest issue at the moment is that their relationship is very different nowadays. Nowadays, VMAP is actually implemented on top of Sandheap. So what we are going to do is actually just to flip their relationship. And there are quite a few problems. So the first thing is that there's another set of API which would translate page struct and virtual address in the hypervisor and from one direction and back. That will be broken by this change. The alternative is to remove all of them, remove all of these APIs, but that would cause a lot of code churn in the code base. And then the second problem is that the core allocator API, xmalloc, are also implemented on top of Sandheap. There is an optimization in the xmalloc function call to return unused pages from a high order allocation. At the moment, we can't implement that optimization yet on top of VMAP because VMAP is unable to unmap a portion of an existing mapping. So that is the problem for us, and I haven't got a clear idea how to solve it. And the third problem is that once we try to implement Sandheap on top of VMAP, it's going to create a code loop in the page table allocation API, which needs to be broken somehow. And this is exactly the major reason for the existence of previous projects. So now, I think you guys should have got an idea about the complexity involved in this project. So by going over and iterate, so even one sentence here, one issue we identify here would create a project on its own. And I think it's rather foreseeable that we would also need to make separate projects for the first two items, but I just haven't got around to do it yet. And then there's another relatively simple project, which is called Implement Persistent Map Infrastructure for Bootstrapping. So this one is a relatively simple one. It's just that the name of this infrastructure is named badly after a similar thing in Linux. But the only similarity is that they both have a smallish address space with some pre-set up page tables. So this project aims to solve a bootstrapping problem. That's because per PCPU mapping infrastructure needs some mapping mechanism to set itself up without a direct map. Unfortunately, this project, this infrastructure is only used during CPU onlining and offlining. It's going to be serialized by a spin lock. It's going to be slow, but we don't really care. So here's the status of various stuff. The legend is that lines written in red means patches are written from scratch for this specific project. And lines written in purple means there are patches from previous attempts of work that are maybe salvageable for certain things. So the DOM-Heap page table project already has 50 plus patches floating around on the mailing list. And I can foresee there will be many other patches for many other projects in the future. And there's really one missing thing I haven't really touched on at the moment. It's the performance. But really, there's really nothing to say because we can't test anything at this stage because nothing works. But my thought is that it may not be too bad, but I could also be wrong. For removing the direct map, because Zen only needs to access a few pages while guest is running, so the operation might be kept to a relatively low volume. And I think there are tricks that we can do to reduce the mapping or napping in the future as well. Specifically for the PV guest table, page table manipulation code is already very long and slow, so I don't think a few extra mapping and a mapping would make a big difference. For the PCPU stack project, the performance aspect, I think it's not going to be noticeable because normally a physical CPU only cares about its own stack during normal operations. So even if we switch to the physical CPU stack, it's not going to be of any difference to a physical CPU from its point of view. So finally, I mean, if you're really interested in this sort of stuff, you can go to have a look at the Jira board for Zen project. There's a card called Zen-119, which can lead you to all of the sub-projects. And then there are also 2 very long mailing list threads, then you can have a look, which contain a lot of details on the code and why certain decisions are made. I mean, just feel free to have a look. And I think that's it. We've got 3 minutes. If you've got anything, any questions? Hello? I mean, you can just say the question. I will just repeat the question. Yeah. I can repeat the question for you. Yeah, so basically, Jürgen's comment is that we should be very careful about the performance aspects of the project, which I completely agree. I mean, in the end, it might be that all this sort of thing is just a waste of time because we can't really reach the performance target at some point. But yeah. Yeah, most of the code is for x86, but for the VMAP, yeah, it's going to affect ARM as well. It's the common code in VMAP. So any other questions? I mean, we should ask Julian instead, no? All right, I think time's up. Thanks, everybody.